Greetings, and welcome to the Introduction to Astronomy. In this lecture, we are going to continue our introduction into astronomy and look at things like some of the numbers that we have to deal with and the concept of light travel time and how we can use that to measure distances. So let's go ahead and get started today. And what we find is that for numbers we look at really big and really small numbers, so we will see a combination of these, and we need to be able to express these numbers in scientific notation. Now, why do we need to do this? Well, the Earth and Sun are 150 million kilometers across. And we deal with numbers even far bigger than that. What we can do is, instead to compress writing out all of those zeros, is to write this as 1.5 times 10 to the 8th kilometers. Now these two are exactly the same, so they express the same number of kilometers. But it is far more convenient to use the scientific notation version. So how do we convert a number into scientific notation? Well, what we do is we move the decimal point until there is only one number to the left, and you count how many places you had to move it. And if you move the decimal point to the left, you get a positive exponent. And if you move it to the right, you get a negative exponent. So whether this exponent here is positive or negative exponent. So whether this exponent here is positive or negative depends on the direction that you had to move that decimal point. Now, let's look at a couple of examples of this. And we will see that. Let's look at a relatively large number and a relatively small number. So here we have the number 314 million. Well, the decimal point, even though it isn't printed, would be here at the end. So we have to move the decimal point how many places? 2, 3, 4, 5, 6, 7, 8, and once we've done that, we have moved the decimal point 8 places to the left. Now, because it's left, that means that the exponent will be positive. So it becomes 3.14. We can drop all the rest of those zeros. And then times 10 to the 8th power, and that represents all of those zeros that we have just gotten rid of. Let's look at an example for a small number. Here, the small number is 0.04563. And we're going to now have to move the decimal point here 1, 2, 3, 4, 5 places to the right. Now this time we've moved it to the right, that means that the exponent is going to be negative. And we write the remaining number 4.563 times 10 to the negative 5th power. So that's how we can convert numbers, and often our first lab will let us look at a few examples, and that is using the meter for length, the second for time, and the kilogram for mass. Now that means that there is a standard units. Now often when you hear me say something, I may give you a conversion into miles or feet or pounds or something, because those are the numbers that those taking the class, at least in the United States, are most familiar with. However, the standard measurements in science are all going to be in meters, seconds, and kilograms, or their different variations. Sometimes you'll see things measured in centimeters for smaller versions, or millimeters, or just grams for smaller amounts of mass. All the other units that we use will come from these, so like velocities can be given in meters per second. So we're using two different ones of these. It's a length divided by a time. Density can be given in kilograms. Bit. Cubic. Meter. Density is a mass kilogram divided by a volume. Well, a volume is the meter but is the third power of that, so such as the volume of a cube is the length times the width times the height. That would give you a third power, or meters cubed. But other units that we use will come from these. Now there are several other basic measurement units, but these are really the ones that we will use. These are the standard ones and the ones that we use primarily in this class. Now let's go ahead and look at some of these distances again. Numbers get very big. The nearest star other than our Sun is 40 trillion kilometers away from Earth. Now that gets to be big numbers and try very hard to comprehend. Now we can write this in scientific notation as 4 times 10 to the 13th, but how can we even imagine 40 trillion of anything? It is a much larger number than our brains like to try to comprehend. So what we often use is the light year is another way of measuring distances, and that depends on the speed of light, which is 300,000 kilometers per second. The light year is the distance that light travels in 1 year. So even though it has year in it is a distance, so it is about 10 trillion kilometers. So that means since the nearest star is 40 trillion kilometers, 1 light year is 10 trillion kilometers. That means the nearest star is about 4 light years away. Does that make the distance any different? No, it's still the same distance, but the number is more manageable. We can comprehend the number 4. We know what 4 of something is, and if we want to compare that to another star that is 6 light years away, we have a pretty good sense of comparison of relative distances. Now let's continue here. And we will see again the light year within our solar system is too big. The Sun is about 8.5 light minutes away. So light minutes, a light year gets us well outside the solar system, so things within the solar system we could use. The light minute would be one example of something we could use here. So let's look at the light minute here. And what we have is. So there's our light minute. We don't often use that, but it is something that would work. We could talk about things being light minutes or even light seconds away within the solar system for things that are close. Typically within the solar system, though, we use what is called the astronomical unit. Now this does not depend on light, but actually depends on the Earth-Sun distance. So the average distance between Earth and Sun here, and that one astronomical unit is 150 million kilometers. So if we want to talk about distances, it's a lot easier to say 1.5 astronomical units than 225 million kilometers. Neptune is 30 astronomical units away. Now why is this more comprehensible? Well, we can comprehend 1 mile better than 5,280 feet or 63,360 inches, even though those are all exactly the same amount of distance. If somebody just gave you without this comparison and just told you something was about 60,000 inches away, you probably wouldn't be able to get a sense of actually how far that was without doing some kind of conversion. The whole idea of using these definitions is to make the numbers more manageable and easier to understand. So what does this have to do with light travel time? Well, we find that light travels at a finite speed. It does not travel infinitely fast. So the light from the Sun gets here in about 8.5 minutes. The light from Alpha Centauri, that nearest star, takes about 4.3 years to get here. The light from the Andromeda Galaxy takes nearly 2.5 million years to get here. What that means is we don't see anything in astronomy as it is right now. The Sun we see as it was 8.5 minutes ago, has it changed in 8.5 minutes? Very unlikely. We see Alpha Centauri as it was 4 years ago. Stars don't change in just 4 years, so it's going to be essentially the same. Even a galaxy 2.5 million years ago is essentially unchanged. Andromeda probably still looks almost exactly as we see it today. But it does mean that we never see anything exactly as it is right now. We never see that object as it is at this instant. So when we start to talk about galaxies, we will be able to see that we can see what galaxies looked like 10-12 billion years ago at the very early history of the universe, simply because their light has taken that long to reach us. So let's go ahead and finish up here with our summary. And what we see is we talked about scientific notation as a way to express both very large and very small numbers. We talked about scientific measurements being made in the metric system of units. And we said that we use distances are so large that we use things like the astronomical unit and light year to measure these great distances. And finally, we talked about how light not traveling infinitely fast means that we can never see any object as it is at this instant in time. So that concludes this lecture on numbers and light travel time. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.